Simple pendulum. Simple pendulum. A simple pendulum consists of a heavy metallic bob suspended by a light, inextensible, twineless string. Light, inextensible, twineless string. To understand the simple pendulum, I have given here a figure. S represents the point of suspension. S represents the point of suspension. O is the center of gravity of the bob, center of gravity of the suspended metallic bob. It is center of oscillation. It is center of oscillation. The distance S to O, it is indicated with L, length of the simple pendulum. It is the length of the simple pendulum. The length will be from point of suspension to the center of gravity or center of oscillation. Capital A represents the straight line distance from O to A. This is displacement of the bob. The point A is the displaced position of the bob. OA is the displacement. A is the displaced position of the bob. mg is the weight of the bob. mg is the weight of the bob which acts vertically downwards. mg cos theta is the radial component of the weight. Radial component of the weight. mg sin theta is the tangential component of the weight. mg sin theta is the tangential component of the weight. OA will be equal to x. OA will be equal to x. When the bob is in the displaced position, its weight mg acts vertically downwards, and this force, the weight of the bob, it will be resolved into two components. One is along the radius, that is mg cos theta. The other one perpendicular to the length of the string in the displaced position. It is mg sin theta. mg cos theta creates tension in the string, and mg sin theta restores the bob to its original position. It tries to restore the bob to its original position. This force will be responsible for the oscillation of the simple pendulum, the bob of the simple pendulum. So, the force responsible or the restoring force is mg sin theta. The restoring force mg sin theta acts towards the equilibrium position. So, it is oppositely directed to the displacement. Generally we consider the direction of the displacement as positive direction. Hence, the direction of the force is negative. Hence, we have taken F is equal to minus mg sin theta. Minus mg sin theta. This restoring force creates an acceleration. The acceleration created by a force F is F by m. So, acceleration A is equal to minus g sin theta. This is the acceleration of the bob when it is at the position A. So, the acceleration will be equal to minus g theta when theta is very small. When theta is very small, this acceleration will be equal to sin theta will be equal to theta, hence A will be equal to minus g theta. We can take sin theta will be equal to theta. Generally we take sin theta will be equal to theta when the angular displacement of the string is less than 5 degrees. The angular displacement of the string is less than 5 degrees. To attain this, we take a long pendulum and the amplitude of vibration will be taken as small as possible. If the amplitude of vibration is small and the length of the string is large, then we can consider sin theta is equal to theta. In such a case, A is equal to minus g theta. But if we consider OA is equal to x, the arc length of the displaced position, then theta is equal to x by L. Hence, A is equal to minus gx by L. In the relation A is equal to minus gx by L, g is constant at a place and length of the pendulum is constant for a given pendulum. Hence, g by L is constant. So, A is equal to minus g by L into x. In this relation, g by L is constant. That means the acceleration of the bob of the simple pendulum is proportional to the displacement of the bob and is oppositely directed. The acceleration of the bob of the simple pendulum is directly proportional to its displacement and oppositely directed to the acceleration. Hence, the motion of the bob of the simple pendulum is simple harmonic motion. We can consider the motion of the bob of the simple pendulum as simple harmonic motion. Derivation of the relation for period of oscillation. Derivation of the relation for period of oscillation. Let us compare the relation for acceleration of the bob of simple pendulum A is equal to minus gx by L. Let us compare the acceleration of the simple pendulum, bob of the simple pendulum A is equal to minus gx by L, which is derived just now, with the acceleration of the particle in simple harmonic motion, which is A is equal to minus omega square x. A is equal to minus omega square x. Comparing these two equations, x is displacement, A is acceleration, and omega is constant. So, instead of omega, we have g by L in the relation for bob of the simple pendulum, for acceleration of the bob of the simple pendulum. Hence, comparing these two equations, we will get omega square is equal to g by L. Omega is a constant. G is constant at a place. For a given length of the pendulum, L is constant. For a given length of the pendulum, L is constant. G is constant at a place. Hence, when we perform an experiment with a simple pendulum of same length at the same place, then G by L is constant. Hence, omega can be considered to be equal to root G by L. Hence, root G by L is a constant. We can use this term instead of omega. Then we will get A is equal to, then we get T is equal to 2 pi into square root of L by G. We know that omega is square root of G by L and T is 2 pi by omega. T is 2 pi by omega. By substituting root G by L for omega, we will get T is equal to 2 pi root L by G. This is the relation for simple harmonic motion, which we learnt in earlier classes. T is equal to, T is period of oscillation, L is length of the pendulum, G is acceleration due to gravity at a place. Hence, the relation for period of oscillation of the bob of a simple pendulum is T is 2 pi root L by G. Loaded spring. A spring suspended from ceiling from a stand, if it carries a load at its free end, which is shown as a colored rectangle, and such a spring is known as loaded spring. A suspended spring which carries a load at its free end is called loaded spring. When this load suspended weight, when it is pulled down and set free, suppose it is pulled down up to the position B, the dotted rectangle represents the pull down position of the loaded mass, and when it is set free, it moves up and comes down. The maximum position or the highest position is represented by the dotted rectangle A. The dotted rectangle A represents the highest position reached by this load, this mass. So, when a load is attached at the free end to a suspended spring and the load is pulled down and set it free, then it oscillates in the vertical plane up and down. Equilibrium position is O, downward extreme position is B, upward extreme position is A. Like this, we have to imagine a loaded spring, oscillating loaded spring. We know that the force, the restoring force in a spring will be proportional to the displacement. The restoring force of the spring will be proportional to the displacement or the increase or decrease in length of the spring. Here, from O to B, the displacement is say minus y. From O to A, the displacement is say plus y. Or the magnitude of the displacement is y from O to B, also from O to A. Then the restoring force F will be equal to minus ky, where k is known as force constant, where k is known as force constant and the restoring force is minus ky. Taking the relation for force as MA, taking the relation for force as MA, then we will get MA is equal to, MA will be equal to minus KY, minus KY. We have the relation F is equal to minus KY, but F is equal to MA, hence MA is equal to minus KY, or A is equal to minus K by M into Y. K is a constant and M is a constant, hence K by M is constant. So A is equal to minus K by M into Y, where K by M is a constant. From this we get the acceleration is proportional to the displacement and oppositely directed. The acceleration is proportional to the displacement and oppositely directed to the displacement. Hence, such a motion is simple harmonic motion. Hence, such a motion is simple harmonic motion. Hence, we can consider the motion of the bob of a loaded spring as simple harmonic motion. Hence, we can compare this relation with the equation of simple harmonic motion. F is equal to MA and MA is equal to minus KY. Hence, MA is equal to minus KY. MA is equal to minus KY. Hence, A is equal to minus of K by M, minus of K by M into Y. We know that, let us compare this equation with the equation of simple harmonic motion, which is A is equal to minus omega square x. A is equal to minus omega square x. Omega is a constant. Here, in this relation, K by M is also constant. K is force constant, M is the mass attached. Both are constants, hence K by M is a constant. So, omega square is equal to K by M. Omega square is equal to K by M. So, omega is equal to root K by M. Omega is equal to root K by M. T is equal to 2 pi omega. We got omega is equal to root K by M. The period T is equal to 2 pi omega, but omega is obtained as root K by M. Hence, T is equal to 2 pi by root K by M. T is equal to 2 pi into square root of M by K. T is equal to 2 pi into square root of M by K. This is the relation for finding the period of oscillation of the loaded spring. The period of oscillation of the loaded spring is 2 pi root M by K. While deriving the relation for period of oscillation of a loaded spring, T is equal to 2 pi root M by K, T is equal to 2 pi into square root of M by K, we have ignored the mass of the spring. We did not consider the mass of the spring. The mass of the spring is ignored. If we consider the mass of the spring and take it as M1, we can derive the relation for period of oscillation, which comes out to be T is equal to 2 pi into square root of M plus M1 by 3 whole divided by K. Square root of M plus M1 by 3 by K. Square root of M plus M1 by 3 by K. This is the relation for period of oscillation of the loaded spring when we consider the mass of the spring also. When we consider the mass of the spring as M1 and the mass of the load is small m. If the spring is elongated by a length x, then the force is equal to minus kx, Hence, the relation for force, the magnitude of the force is kx. This will be equal to the weight mg of the bob. Hence, k is equal to mg by x. So, we can replace k with this value. The relation for period t is equal to 2 pi root m by k. The relation for period t is equal to 2 pi root m by k. Replacing k with mg by x, we get t is equal to 2 pi into square root of m divided by mg by x, which is equal to 2 pi root x by g. T is equal to 2 pi root x by g. The relation between force constant and length of the spring. We know that the the force constant is inversely proportional to the length. So K is inversely proportional to the length, or K is proportional to 1 by L. If we divide this length of the spring into two springs of lengths L1 and L2, the spring is divided into two parts whose lengths are L1 and L2, then L will be equal to L1 plus L2. Since K is proportional to 1 by L, KL is constant. KL is constant. Hence, if K1 is the force constant of the length L1 and K2 is the force constant of length L2, K1 is force constant of length L1, K2 is force constant of length L2, then K1 L1 is equal to K2 L2 is equal to KL. K1 L1 is equal to K2 L2 is equal to KL. From this relation, we get K1 is equal to KL by L1 or K into L1 plus L2 by L1. K1 is equal to KL by L1 or K into L1 plus L2 by L1. K2 is equal to KL by L2. K2 is equal to KL by L2 or K2 is equal to K into L1 plus L2 by L2. K into L1 plus L2 divided by L2.